right. So thanks everyone thanks a lot for the opportunity. So I'm doing two experiences today. One is to give a talk on my balcony because people are breaking the apartment next door. So it's a little bit noisy sometimes. And if you cannot hear me, let me know. The other thing that I'll do is I'm going to try to do some semi-blackboard talk. So let me know if that does not go well as well. But what I want to talk about is on the mass ordering. So recently there was the Neutrino 2020 conference and a few things changed, and it changed in a, I would dare to say, in an unexpected way. And this is what I'm going to talk about. So let me start. So the first thing that I want to tell you is that I understood that several of you are not neutrino physicists. So let me tell you about beam neutrino in like 3 minutes, because this is one of the most important things that we are going to discuss here. So beam neutrinos, the way you produce them is basically via QCD. So you shoot a beam of protons on a target, right? And then QCD creates a bunch of pions and kaons and other mesons. Doesn't really matter which other ones. Let's just focus on the pions. So you know that pions will decay mostly of the time to muons and muoneutrinos. And this is how you get your neutrino beam. To optimize things, you make a system that creates it's a magnetic horn system. And this magnetic horn system essentially focus the pions that you want to be focused, say the pi pluses. Then they go through a decay pipe. And in the decay pipe, well, they decay. And they decay mostly of them to mu. And let's just do this, nu mu. And then after the decay pipe, you have something just to absorb these guys, to absorb the muons. And you have dirt as well, which will help absorb them. So in the end, after the dirt, you have a beam only of nu mu's. Of course, that life's not perfect. Some pions will decay to muons, but then the muon will further decay to nu mu bar and nu e. Also, sometimes you produce kaons, and kaons also decay to nu mu bars and nu e's, etc. So you always have some contamination here. But the deal is, you produce these guys. Now you have a beam of mostly nu mu's. And one of the major things we want to measure is CP violation. So the major channel in beam neutrinos to measure CP violation is by comparing the nu mu to nu e appearance versus nu mu bar to nu e bar. So in a very, very naive way of doing things, let me just tell you what would be like the probability of oscillation for 2 neutrinos. Imagine that you only had 2 neutrinos. So the probability would typically go, let's say for nu mu's to go to nu e's, would typically be something like a sine square of a mixing angle, and then an oscillation phase. Let me know if you cannot read my handwriting as well. And if you have any questions, just stop me at any point. So the nice thing about this, so this is for 2 flavors, right? The nice thing about this is that you can see here, for instance, the first thing you see, here, is that this is a sine square, which means that the sine of this delta m square does not play any role here. So if you are in vacuum and you're looking at a 2 neutrino framework, the sine of delta m square cannot be measured. And the way you measure the delta m square itself, so this is the mass split in between neutrinos, right? You have, let's say, mass 1 and mass 2. And delta m square is essentially m2 minus m1 square, for instance. So the way you measure these guys is you produce these neutrinos, you look at some oscillation physics, say, let me draw the nu mu to nu mu oscillations here, which is much easier for me. And what you see is something like this, where this minimum here, so this height here is related to the mixing angle. So let me pull an arrow. And this minimum here is related to the delta M square. Okay, you know the baseline, the L, this guy here. You determine the neutrino energy somehow. Let's not worry about how right now. And this gives you the mass splitting. So this is how you do neutrino physics in a nutshell with beam neutrinos. Now, what we're going to talk about is the mass ordering. So let me define for you the mass ordering. So by looking at things like this kind of probabilities, we have seen oscillations consistent with 2 oscillation frequencies, right? So we have 2 oscillation, sorry, here's better, frequencies. One is called the solar splitting, delta M squared 2-1, which is about 7.5, 10 to the minus 5 EV square. And the other one is the atmospheric splitting, which is delta M squared 3-1, which is 2.5, 10 to the minus 3 EV square. And you see that one of them I put a plus sign explicit. The other one I wrote the models because you don't know the sign. Now, how do we figure out what is the sign of these mass splittings? And this is one of the very few formulas that I'll give you here in this talk. So when you are calculating neutrino oscillation, the important quantum mechanical quantity that you have is the Hamiltonian. And in 2 flavors, you can write the Hamiltonian like this. So this is oscillations in vacuum. And now you add here a term that has to do with how matter changes your oscillation frequency. So basically when neutrinos cross matter, they feel like a refraction index, and that changes their behavior, their oscillation behavior. This U matrix here is the PMNS matrix. Of course, that here I'm doing 2 flavors. So let's say that this is just some cosine, sine, minus sine, cosine. And this guy here is what we call the matter effect. So you see that now, if you just open up this calculation very quickly, you have this guy is the neutrino energy. You have the matter potential, and then there's a matrix like this: cosine square, cosine sine, cosine sine, sine square. And now you see that the sign of this guy, it becomes important because this term here distinguishes between a plus and minus a plus and minus term in this side. So basically, by looking at matter effects, you can actually infer the sign of the mass splitting. So now what you do is that you look at solar neutrinos. And in solar neutrinos, well, life's a little bit complicated, so I'm not going to go into detail here. But what you see is something like this. You have the probability that a nu-E remains a nu-E. And these neutrinos have energies around the MeV scale. And this probability goes like this, where this region here is dominated by oscillations in vacuum. So basically, whenever the energy is very small, this first term, because it's 1 over energy, becomes much larger than that guy. So you say that the matter doesn't really matter. So you're doing oscillations in vacuum. And this is what you would observe with solar neutrinos. And down here is oscillations in matter. And this guy down here is sensitive to the sign of the delta M square. And this is how we have measured, well, not exactly how we have measured the absolute value of the solar splitting, but how we have measured the sign of the solar splitting. Of course, you need to combine with a few other experiments just to, kill some degeneracies, etc. But I'm not going to go into that. And the whole point is that this has not been done for this guy, for the atmospheric splitting. This has been done for the solar splitting, but not for the atmospheric one. And the reason is just because whenever you're looking at atmospheric neutrinos, the matter potential that you need to see some effect like in the sun would be very large. So it's difficult to see that. It's just very challenging, okay? So the mass ordering is essentially the question of what is this sign here. So just to set up notation, we have the normal mass ordering. We can define the normal mass ordering. And it's basically when neutrinos would be like this, 1, 2, and 3. This guy here would be your delta m square, 3, 1. And this little one here is your delta m square, 2, 1. Just pop this guy a little bit to this side. And the inverted ordering would be when you have 3, 1, 2. Again, this guy here is your delta m square, 3, 1. And this little guy here is delta m square, 2, 1. And you see that here, this guy is negative, right? This guy is positive. So this is basically the mass ordering. One question you can ask is, well, 1, 2, and 3, these are just labels. So it's kind of dumb to say, like, to try to order arbitrary labels. But these do not need necessarily to be arbitrary labels. You can say that nu1 is the neutrino with highest nu-E admixture, while nu3 is the one with lowest nu-E admixture. So basically, when you say, I can define physically what is my nu1, nu2, and nu3, where nu1 has the highest admixture of nu-E. And if I do that, then there's no arbitrary convention here anymore. And I'm still left with these two cases of normal and inverted ordering. Okay, so before going to the data, let me just tell you why we care about this ordering. I'm pretty sure that most of you know it, but let me just go through it. So one important business that the ordering, the neutrino mass ordering has is on cosmology. So when you look at CMB, the total mass on neutrinos, the total energy that neutrinos carry away from structure can actually change CMB quite a lot. And you can see the effect here in this paper. Basically, CMB is sensitive to the sum of all neutrino masses, right? It's basically the sum of all neutrino masses below. Well, there is some discussion here, but let's say that this thing ranges from 0.1 to 1 electron volt, depending on who you're talking to, if you're talking to a cosmologist or to somebody else like me who doesn't know what they're talking about. So cosmology is very sensitive to neutrino masses, and future experiments will actually be able to, could be able to disentangle these two scenarios here. So in some sense, you want to measure neutrino masses with oscillation physics, because that will give a very good cross-check of what is going to happen, what is happening in cosmology, right? So if you want to do precision neutrino physics, we need to measure the mass ordering. The other point is when you try to measure neutrino masses with kinematics, like in scattering. So in scattering, basically you have a tritium nucleus that decays into helium, neutrino, and electron. And the spectrum of tritium beta decay is very well known. In the end point of the spectrum is sensitive to neutrino masses. And this is actually something that was predicted, was pointed out actually by Fermi in his paper on, I don't know, 30 whatever, in his old paper. So that's something that we are still trying to measure. But just to show you how the ordering is important here, the quantity that we're sensitive to is this effective electron neutrino mass, which is basically this sum. And just to give you a few idea of numbers, if you look at the elements of the PMNS matrix squared, they go like 2/3 up here. So this is the E1, 1/3 for the E2, and about 0.02 for E3. This is very, very schematic. Huh? So when you have the normal ordering, so 1, 2, 3, you see that this guy here, which is the big mass, is being multiplied by the small number. And these guys here who are the small masses are being multiplied by the big number. So that's terrible. If you have the inverted ordering, let me do here, then this would be 1, 2, and 3. And now you are multiplying the big guys, the big masses, by the big numbers. right? So Catherine would have a much easier time if the hierarchy, the ordering is inverted. And the last thing that I want to tell you, or maybe, yeah, I think this is the last I want to tell you here, is on neutrinoless double beta decay. So on neutrinoless double beta decay, what you have is some of these, some nucleus, they cannot undergo beta decay because the energy is I don't know if I have space here, but let me just do. So this would be, what is this? This is Z for a fixed A. And this is the energy of the, or the potential of the binding energy of a nucleus. And you would have something like this, where your nucleus cannot go beta decay to another state because the other state has a higher energy, but it could actually go double beta decay. And there is the possibility that in double beta decay, if neutrinos are Majorana particle, they actually, in some sense, they annihilate each other. So you start with a neutron, 2 neutrons, you end up with 2 protons. And instead of having 2 electrons and 2 neutrinos, these neutrinos sort of annihilate each other. So they're virtual neutrinos. And this is proportional to what we call the neutrinos double beta decay effective mass, which is m beta beta equals, I guess it's UE1 square m1 plus UE2 square m2 plus UE3 square m3, where all these guys here have phases, right? So basically you have 3 complex numbers being summed up, and now you want to see if you can, if this m beta beta is large enough, so that would enhance the rate of neutrinos double beta decay. And what happens here is that, again, from the argument of the previous slide, this guy here is about 2/3, 1/3, the modulus of it, and 0.02, and this is normal ordering, 1, 2, 3, and inverted ordering, 3, 1, 2. And now you see again that if you have this kind of ordering, you're multiplying the big mixing by small masses, so you're here, right? If you have this order, you're multiplying the large masses by the large mixing, so you're up there. So that makes inverted ordering a much better scenario for measuring neutrinoless double beta decay, so measuring a lepton number violation. Okay. Now, regarding oscillations, I apologize for the formulas, but this is probably one of the very few formulas that I'll give you here. I think this is probably the only one. The only slide with formulas. Maybe I'll repeat this slide one more time, but I assure you that we're going to be very light on formulas here. So when you look at the nu to nu oscillation probability, there is a term here that, so this guy's here, delta, I think I did not define here, delta, square ij is defined as delta m square ij L over 4 E. So that's basically the oscillation phase. And you have one term, you don't need to care about all the details, but you have one term that is the leading term, which has no intrinsic CP violation. So a CP violation comes in this Yarskog invariant here, but it has this A, which has something to do with matter effects. So this guy here has something to do with matter effects. And just to give you the idea of the numbers, I'm putting what is the size of A times L, which is the quantity that always show up here, for vacuum, which is 0, T2K, NOVA, T2 hyper KK, and Dune, okay? So the important point is that this guy here depends on matter effects. This guy here depends on the intrinsic CP violation, the leptonic sector. And this term here is basically what we call the solar term. So to make this discussion a bit shorter, we can plot something that is very useful to understand these things, which is called a biprobability plot. Biprobability plot. And usually in these plots, you fix an experiment, you fix an energy, and you look for you plot in one axis the nu to nui probability, and on the other one the nu bar to nui bar probability. when you change nu mu to nu e, so when you change neutrinos to antineutrinos in this formula, your J goes to minus J, so the R-square change sign, and AL goes to minus AL, okay? So what you have here, so let me just draw a line here to help me, is, hopefully I can draw these things properly. So you start here, you fix, let's say, all oscillation parameters, and you only let delta vary. So when delta CP is equal 0, you are in a point here where you have some nu mu to nu e oscillations and some nu mu to nu e bar oscillations. And now as you vary delta, you run through this ellipse going like pi over 2 here, pi over there, and then 3 pi over 2 here. And this would be for normal ordering. When you flip to inverted ordering, because of the matter effects that can in some sense see the sign, your ellipse is somewhere else, inverted ordering, where you start here at 0 and you go to pi over 2 here, 3 pi over 2. Oh, sorry. It's only pi, and then here 3 pi over 2, okay? So now, just a few more details. The size of this ellipse here is based on this large axis is related to the sign of the solar delta m square. And if you change theta 2, 3, this ellipse go in the axis direction, okay? Also, the separation between ellipses has to do with the matter effect. And we'll see an example of that very soon. So the point is, imagine that your experiment measures nu mu to nu e in neutrino mode and in anti-neutrino mode. So it draws the data point here. So you see that this is important. The importance of having neutrino and anti-neutrino is because if you only measure, say, neutrinos, okay? So say that you only measure neutrinos and you are compatible with some region here. So you're compatible with like anything basically. But at the moment that you measure antineutrinos, okay, let me change the color of this. At the moment that you measure antineutrinos, now you're looking at the overlap between these regions, right? This guy here. And now you can actually tell the hierarchy. You can say something about the octant of theta 2, 3, and you can say something about delta CP. So that's why this biprobability plot is so important to understand, because it basically conveys you what the experiments are measuring and how that translates into delta CP, hierarchy, and theta 2, 3 octant. So okay, so let me get to some data, right? So before Neutrino 2020, why do I have this? I don't need this. Before Neutrino 2020, we had the following results from NOvA and T2K. So NOvA measured nu mu to nu e appearance and nu mu bar to nu e bar appearance. Okay, and they saw, well, they obviously saw evidence of appearance in both neutrino and antineutrino modes. And if we just look at their event numbers and we translate into, apologies, into a plot like this, you just multiply the probability by quantities that translate into event numbers. If you do that, this is what the old result from NOvA. Okay, so this is number of neutrino events, number of antineutrino events. So you can look at this like nu mu to nu e probability, nu mu bar to nu e bar probability. This is normal ordering. Some people use H for hierarchy. I use ordering, but that's fine. Normal ordering, inverted ordering. And here you have the data point of NOvA. And you see that NOvA is basically, the data point is basically on top of everything. It was on top of everything, right? So when you look at what are the values of delta CP that fit the NOvA data better, you can see here for normal ordering that almost any value fits well. This is like 1 sigma, so any value is fine. And inverted ordering, so inverted ordering, it's a little bit less preferred, but you know, there are still some regions where you basically have less than 2 sigma rejection, right? So basically NOVA was compatible with almost any CP violation in either hierarchy. Now, if we look at what happened with T2K before Neutrino 2020, so that's basically the same plots from the Nature paper. In the same kind of plot, the NUMU to NUI events, NUMU bar to NUI bar events, you can see that the NOVA measured data is actually quite far, well, somewhat far from the allowed region in the standard model. Okay, so this is actually why T2K preferred so much maximal CP violation here, because actually the data point is away from everything. Okay, I hope you're not hearing too much background noise. Let me know if you are. And I hope you are still with me. Are you still with me?
Yeah, we're all still here.
I think you're still with me. So, okay, so this is why T2K preferred minus pi over 2 for the CP violation. And you can see here in these plots, for instance, here is normal ordering preference for CP violation 1 sigma and 3 sigma. And you see that T2K basically almost rejected no CP violation at 3 sigma. And for inverted ordering, you don't even have the 1 sigma region here. So combining these two guys together, you see NOVA gives you this, and T2K gives you that. So in some sense, it's easy to see that NOVA is roughly compatible, not so far from minus pi over 2. T2K is only compatible with minus pi over 2. So when you combine these guys, you can do a global fit, and this is what you get. So this is a result from the old NuFit data, the old fit from the NuFit group. And this is the chi-square for the global fit for delta as a function of delta CP for normal ordering and inverted ordering. Don't look at the dashed lines for now. The solid lines here is basically normal ordering, all data without atmospheric neutrinos. And this one is the same, but for inverted ordering, okay? So you see that normal ordering is preferred, and inverted ordering is actually rejected at, let's see, I don't know, delta chi-square of 6 or so. Oh yeah, they have it written up here. Delta chi-square of 6. So there was somewhat of a strong preference for normal ordering only coming from everything but atmospheric neutrinos. When you add atmospheric neutrinos, it adds more on top of that. And then the preference for normal ordering was about a little bit above 3 sigma, okay? So now what happened at Neutrino 2020? At Neutrino 2020, the NOVA data slightly moved, but not much. So it's very much compatible. Let me show you the previous data. You see here, close, you know, kind of touching the inverted ordering and right in the middle of the blue ellipse. Here is kind of almost the same, right? So it didn't change much. So basically for NOVA, everybody here is still fine, right? All the values of delta CP. But for T2K, let me jump this one. For T2K, the data point moved much closer to the standard model. I'm terrible in drawing this. I apologize. Much closer to what is allowed by the standard model. And the important thing is to note the following, that in T2K, if you look at the normal ordering fit, the preference of T2K is for minus pi over 2, right? So this is minus pi over 2, which is also 3 pi over 2. This is delta CP, okay? And when you look at NOVA, if you look at the 3 pi over 2 for normal ordering, there is a 2 sigma tension in the data. The question is if there is any other point that would fit this data better. And if you look back here at T2K, T2K also prefers the same CP violation for inverted ordering. But if you look at here NOVA, inverted ordering actually gets a much better agreement with the data. So what happens is that these experiments, if you look here, NOVA slightly prefers normal hierarchy. T2K is strongly, maybe not strongly, but also prefers normal hierarchy. But their combination do not prefer normal hierarchy. And let me just spend a few more minutes on this, and then we can finish this. So going back to my slides on the equations, from these expressions, there are two things that one can do. So remember, delta 31 square is defined as delta m square 31 L over 4E, and the same for delta 21. This guy here is the matter effect. This guy here is the Yaroskog. So that measures the amount of CP violation. And you have the size of the matter effects for particularly NOvA and T2K, okay? So if you take this, two, these probabilities here for neutrinos and antineutrinos, so when you do antineutrinos, the Yaroskog flip sign and AL flip sign, the matter effect flip sign, when you get these expressions for neutrinos and antineutrinos, there are two important quantities that you can do. One is the sum of probabilities, and the other is the difference of them. So basically, this would be P mu E minus P mu E bar. So that's the delta P mu E. And the sum P mu E is obviously P mu E plus P mu E bar. And now you see that when you sum these guys, I told you that what flip sign is the Yaroskog and AL. When you sum these guys, the dominant term will be this one, because this term that there's almost no dependence with AL, very little here, because this sign is close to 1. So a small change here will not change the results very much. And there's no Yaroskog here. So that means that when you do the sum of probabilities, most of it is a CP conserving, mostly CP conserving sum. So most of it comes from the leading order term. And then there's a small amount here that is sensitive to a CP violation. But when you do the other guy, the difference, there is a large term that, apologies, sorry. There is a large term here that comes from CP violation, and a small or relatively small term that comes from, it's not small, it's comparable, but this comes from matter effect violation, right? So this matter effects and this intrinsic CP. This one here is the leading term, and this guy here is a little bit of matter effect and intrinsic CP, but fine. So with these two quantities in mind, we can plot a bi-probability plot based on these guys, and what we see is very interesting. So here, oh, I apologize. I'm showing. Okay, let me just jump there. So here you see the sum of these guys for NOvA and versus T2K, and the standard model predicts very, very little changes. Well, it depends exactly on what are your parameters of oscillation. So if you go back here, you see there is a theta 2, 3 here. Where's that? Delta m the sign of delta m square. So that's the hierarchy, etc. But you see that there is a very small dependence on the oscillation parameters on delta CP. So basically, the data point before Neutrino 2020 here and the data point after Neutrino 2020 are essentially in agreement. But when you look at the difference, so this is NOvA and this is T2K, these are the ellipses for normal ordering. And you see that before, your data point was touching these ellipses. And now the data went away from the normal ellipses. So now they're going away from normal ordering. And this is inverted ordering. And you see here, well, if I could draw, but I'm not sure if I, oh man, this is a terrible drawing. But you see that the data kind of overlaps with the inverted order, right? So that shows you why inverted ordering became preferred. If you want to see the bi-probability plots for each of these experiments, I have them here, but I'll just keep that if there are any questions. So now that we have this, we can actually go and do like a decent fit of these data sets. And this is our final result on this fit. So this is a little bit of a busy slide, but you have here. So where do we start? Let's see. We have here the delta chi-square as a function of delta Cp. Okay, up here. So solid is normal ordering, dashed is inverted ordering. So let's look at the solid. T2K, let me write here, this is T2K in red and NOVA in blue. And you see here that if you look at delta chi-square as a function of delta Cp, for T2K who is red and NOVA who is blue, you see that for the normal ordering, which is solid, T2K prefers this region here. You see the red line touching the axis, but NOVA rejects this region. So there's some sort of tension in the data. But when you look at the inverted ordering, everybody rejects this guy here, but both T2K and NOVA, look at the dashed lines, they all prefer the same value of delta Cp. So when you look at T2K alone prefers normal ordering, NOVA alone prefers normal ordering, but their combination, because of this small tension, it actually prefers inverted ordering. So that was the point that I was making. And you can also see the same thing here in this theta 2-3 versus delta Cp plots, where T2K prefers this region, NOVA prefers that region. And so there is a tension. When you look at normal ordering, they are perfectly compatible. Does that answer the question?
One other question I had was, I think it was the previous slide. Just, is there a prior that that any data points on the right should lie on the one-to-one, that these two probability differences should be the same regardless of the experiment?
Well, no. The probability is, so, okay. So if you go back here to the formulas, the asymmetry here in probability, there are two terms, one that comes from intrinsic Cp, but there's another one that comes from matter effects.
Yeah.
And since the matter effects for T2K and NOVA are different, you would expect them to be different for T2K and NOVA. And this is what you see here, let's say for normal ordering, you see NOVA goes from 0 to maybe 0.45, while T2K goes from -15 or so to 0.03. So there are slightly difference. There is a slight difference between NOVA and T2K, but the prediction of the standard model should be on top of these ellipses, given that you measured all other oscillation parameters. They don't change very much where these ellipses are. So this is basically why before Neutrino 2020, there was a strong preference for normal ordering because you're far away from the inverted. But now you move it slightly to that region, which makes you closer to inverted and far away from normal. Is that okay?
Yeah, thank you.
All right, so what I was saying here is that individual experiments do prefer, the T2K and NOVA, they do prefer normal ordering, but the combination prefers inverted. And the other thing you can do is to add atmospheric neutrinos. So this is atmospheric neutrinos. And atmospheric neutrinos do have some preference for normal ordering, right? So a positive delta chi-square here means normal ordering, negative means inverted ordering. But you see, if you just compare this result with, so this is with the old atmospheric data before Neutrino 2020. But if you just compare these guys to the previous global fits, the delta chi-square before Neutrino 2020 for normal ordering was of order 10. And now the delta chi-square for normal ordering became of order 2. So essentially, the preference for normal ordering is completely gone. And I think that's the main takeaway message from this talk. I also have the same plots here with whenever you add atmospherics. So this guys here, it's basically T2K plus NOVA plus atmospherics. And you can see that when you add atmospherics down here, you still prefer normal ordering just because of atmospherics. But you know, at 1 sigma or so, these guys are pretty much compatible. So that brings me to my conclusions. So basically, I hope I convinced you that the previous strong hint for the neutrino mass ordering is completely gone. Of course, if you look at the current results from global fits, there is still some preference more than this delta chi-square of 2 that I showed you. But this is just because you combine reactor experiments with accelerator experiments and atmospheric. And then when you get all these 5 experiments of T2K, NOVA, Diabase, Reno, and atmospheric, so these 5 data sets, they all contribute comparably to give you like a sort of a 2 sigma hint. So in my opinion, this becomes a much more fragile statement. So I would still say that the strong hint for the mass ordering is gone. And in my opinion, this is excellent news for Catherine, for neutrinos double beta decay, and even for Ptolemy. And it makes the future experience much more important. So thank you. If you have any questions, I would be happy to answer them.
Thanks, Pedro. Yeah, so if you have a question, go ahead and raise your hand. So Alex, right? Has a question? Why don't you go ahead?
Yeah, so I'm a little bit confused. So if I look at your slide 20 or slide 21, so before neutrino, there was a few sigma preference for normal ordering, and that's gone away. I'm still a little bit struggling to understand how changing an experimental measurement by less than 1 sigma changed the global fit by many sigma. It feels inconsistent.
I don't think it's less than 1 sigma, right? It's just because you see, I think the idea is like here, no? The experiments changed, but there were 2 things before that were pointing into normal ordering. So the first one is, let me go back to the old data. Where's the old data? So the first one is, if you look here into NOVA, NOVA is more compatible with normal order, even if it's just a little bit, but especially with normal ordering at 3 pi over 2 is not so far away. And T2K, it's actually incompatible with the standard model. Of course, this is like a 1 sigma statement, 1.5 sigma statement. It was incompatible with the standard model, which meant that you need to go to the extreme point here. So you need to go to normal ordering maximal CP violation. Now, not only NOVA moved closer to the inverted hierarchy, inverted ordering, and now inverted ordering is perfectly compatible with NOVA, but also T2K moved. And you see, let me show you T2K. I apologize for these things to be so far away, but you see here, you're probably like 2 sigma away from inverted ordering, okay, in T2K, no T2K data. But with this new data, you're actually almost touching it. So inverted ordering is not so bad anymore, okay? So basically what you have is that actually 2 experiments are pointing the same direction now. 2 experiments started pointing more into inverted ordering. And even in the normal ordering, what these 2 experiments prefer is not compatible. So in some sense, you are like losing 3 times. NOVA, it moved a little bit closer to inverted. T2K moved a little bit closer to inverted. And the combination of these experiments now do not want normal anymore because they're in tension. So I think this combination of these 3 effects is what is giving you, is taking away the strong hint for normal ordering. There is also one thing to say that is important, that when you look at global fits, the global fits do not involve only these experiments, right? Which are like the obvious candidates for measuring CP violation. The global fits have, I have a few extra slides here that I can write. So the global fits have T2K, NOVA, Diabase, Reno, double show, and atmospherics. And the reason why I write all these guys is because these guys here, they measure what we can define as delta m square mu mu with the disappearance channel. These guys here measure the delta m square EE, and the difference between them is related to the ordering. So that's another way of measuring the mass ordering. And what happens for the current global fit is that the Reno experiment, it's basically what drives the entire global fit towards normal ordering. So if you look at, this is going to be very schematic, but if you look at the delta m square 3,1 with a minus sign, you would have, let's say, T2K, NOVA, I don't know, Diabay, and then I need some other color. There's like Reno away, very far away from these guys. This would be delta chi-square, which means that Reno is actually introducing a tension in the inverted ordering. But again, you know, now you're combining 5 or 6 data sets to be able to get like a delta chi-square of about 4 or 5. And in my opinion, this is a little bit more fragile because these fits are not done by collaborations, right? This is like people like me trying to reproduce experimental data the best they can without all the details. So if you just look at T2K and NOVA alone before, where is that? Here. So, or actually all experiments without atmospherics, you had a delta chi-square of 6 in favor of normal. And now you have a delta chi-square of about 2 in favor of normal. So that's mostly what is happening here. Sorry, I thought I said 6. It's actually 10, no? Because here I'm comparing with atmospheric. So the right comparison is 10 to 2 or 6 to minus 2, right? This is without atmospherics. So I think to answer your question, it's just a combination of 2 experiments moving towards the order hierarchy and on top of that, introducing a tension for the normal one.